Welcome, everyone, and to our 26th meeting. We've been going quite a while. Let's get started, and let me hand things over to John.
Well, thank you, Dave, and good morning, everyone. Good afternoon, good evening, wherever you may be. Thank you very much for joining us today. As Dave just mentioned, Zoom meeting number 26, and I guess by all accounts, our little Ivan Zoom meeting experiment is has caught on, and looks like a very good attendance today. Very interesting subject material, and thank you in advance to our speakers. Also, thank you to our sponsors, Q1 Instruments and MR Resources. MR Resources, of course, been around for 37 years now, and they do quite well with servicing NMR system relocation. And especially, I wanted to point out today annual service contracts that for any Varian Agilent instruments that you might like to consider putting under contract. Obviously, little or no service for those instruments these days. And also the broker systems as well. They offer full coverage, once again, with annual service contracts. And our sister company, Q1 Instruments, a little bit more of a newcomer to the industry. Just a couple of words on Q1 Instruments. Very, very capable lineup of 400, 500, and 600 megahertz NMR systems. Stand up in specifications and performance every bit as well as the competing models. And please do have a look and contact them for complete systems and also console upgrades. Any older Varian Agilent consoles that are going to be replaced, have a look, and certainly well worthwhile having a look at. Anyways, that being said, thank you very much to our sponsors today. I wanted to mention briefly the live upcoming Ivan pre-ENC meeting to be held in Orlando, I believe, April 23rd, if I'm not mistaken, the day before ENC. Planning a live sort of a hybrid event. Will be also telecast by way of Zoom and I believe on YouTube as well. But let me hand things over to Krish. Oh, I also wanted to mention the Ivan Founders Award, looking for nominees for this year's annual award. Let me hand it over to Krish, and Krish, if you could give us a little bit more information on that and other upcoming meetings, please.
Thanks, John. Welcome, everyone. I want to talk a little bit about what is coming down the pike in the workshop series. The next one we are looking at on March 24th, 4 weeks from now. Professor Patrick Girardot from Nantes will be leading a panel of experts on the topic of QNMR, but beyond proton spectra. Then, as John mentioned, we do have ENC user conference in April, Ivan conference. That's on the 23rd of April. We have a very interesting lineup of speakers. It's going to be hybrid. You can attend if you are in Orlando. You can attend in person. If you are unable to come to Orlando, you could still attend virtually through our virtual process that we are working out as we speak. That lineup is coming together. We should be announcing it in about a week or so, I believe. And we also have Ivan, planning Ivan Hour, exciting, new, interesting idea. Hear from us soon on that again in a week or so. We will have a little bit more details by email. Beyond that, in terms of workshops, starting May through July, we have 3 workshops planned. Molecular confirmation via NMR, revisiting again, forensic NMR, We also have polymer NMR topics, a couple of new ideas that are brewing at this point to fill August and beyond. And so I think we continue to have an exciting lineup with all your support in attending those. Thanks. With that, I will pass it back to John. Thank you, John.
Thank you, Krish. And as everyone can see, we've got quite a number of meetings planned out for several months into the future. Once again, the live upcoming meeting, please do join us either in person or virtually. All that being said, I will turn things over to Dave. And Dave, if you could start the engine for us here and kick things off, please.
Okay, let's get started. And so Michael Bernstein, our panel leader, I'll turn things over to him and he'll introduce the two other panelists.
Okay, hi everyone, and welcome to the scientific portion of today's meeting. It's very kind of you to join us. I think we've got a super selection of speakers today. So my name is Mike Bernstein, and I have a long association with QNMR as it applied to pure small molecules and mixtures. Working in pharma, I also worked on kinetic analysis of chemical reactions, which we call reaction monitoring as well. And when I worked at Lab, I helped develop capabilities to enable access to these challenging spectral data sets. So we have two very talented speakers today who are going to speak to the title theme, which is Advanced NMR Analysis Methods for Challenging Spectral Data Sets. So the way it's going to work today is that I'm going to give a short introduction to the whole topic, just to get everyone seated and on the same page. And then that'll be followed by Dan, who's going to follow with the portion that relates to the software. So his talk is entitled Quantum Mechanical Modeling. And then we'll pass the baton to Eric, who'll pick up on the same topic and describe some process analyses that he's done using those software tools. Okay, so reaction monitoring is a kinetic analysis of a chemical reaction or process. So we won't be discussing today hardware, but the aim of reaction monitoring is to determine the concentration of each chemical compartment as they change with time through the course of the chemical reaction. That is, multiplets must be chosen and their areas determined. So data processing and analysis shares a lot with QNMR of mixtures. So there are constant data processing and analysis challenges that must be met. So the software analysis should be automated and fast, and preferably in real time as the data are acquired. As with any quantification procedure, the spectrum phase and baseline must be optimized for each and every spectrum. And the reaction monitoring spectra themselves are often quite complex. Multiple species can occur from reactants, intermediates, products, and byproducts. And spectra are generally recorded in protic solvents, creating problems with dynamic range. Each species must be identified before integration, and that can present challenges. So here we see an example data set of spectra recorded whilst the chemical reaction is taking place. Immediately obvious challenges are seen from intense solvent peaks, which have shown, which are grayed out and removed from the analysis. Dynamic range and signal noise difficulties that follow from integration of low-level species, which you can see, for example, over here. And peak horrors, such as changing frequency and line width that you can see from the species that doesn't quite know where it wants to resonate. So peak frequency changes seen in this data set require an automatic sum integration method that refines the optimum integral limits for each spectrum. So the same spectral width, the same integration width is used for each time, but it's repositioned to follow the peak as it moves through time. This is quite a simple case, really, but and things are not always that simple. So here we see a spectral data set that represents the difficulties that can occur. So the spectrum is complicated by these large, broad peaks that are scooting around the spectrum and misbehaving and causing havoc. And also the fact that the signal to noise ratio is rather low. So it's difficult to get sensible sum integration data for the 4 sharp peaks here at 3.9-ish. So you get this sort of horrible mess over here because of the interfering large peaks. However, when we do a deconvolution procedure, we can pick out the 4 sharp peaks and ignore the contribution from the others. And in that way, we can get a very reasonable build-up curve for the species as represented by these 4 peaks. So let's take a closer look at spectral deconvolution and see how it's performed in very general terms. We'll be going into huge detail, mainly in Dan's talk. So there are very many ways to deconvolute lines, and they mostly have similar algorithmic issues to address. So here's a classic implementation for standard line deconvolution. And the starting condition was always that the line positions are known and that reasonable estimations of peak height and width are presented. So the algorithm must also have a mathematical expression for line shape. And here it's a combination of Lorentzian and Gaussian functions, but you're not restricted to that. So an iterative fitting starts with a simulated line. And so the blue line is the simulated one, dark blue line. And the residual error is calculated for this versus the real line. And that's shown by the red line at the bottom. So that's the residual error. And practically the fitting process, so the fitting process is one where these parameters here are changed so that the residual is minimized, and the fitting process ends when the residual error is basically asymptoted to a small value. Practically speaking, the fitting process is aided if constraints can be applied. For example, how much this peak position can change, or how much the peak width is. And I've represented this by this lock values as well, where you can set something to have a constant value. So I'm keeping my presentations really short because the really interesting part of today's agenda is the 2 presentations from our speakers. So this ends my introduction, and I'm going to introduce our first speaker. So our first speaker is Professor Daniel Holland from the University of Canterbury in New Zealand. Very early in the morning for him, so we thank him for getting up to join us. And his talk is entitled Quantum Mechanical Modeling for Quantitative Benchtop NMR. So Dan is a professor of chemistry, professor at the University of Canterbury, where he's also the head of Department of Chemical and Process Engineering. He studied chemical engineering at the University of Canterbury before heading to the UK to complete his PhD at the University of Cambridge. Whilst there, his research was primarily focused on NMR imaging and the use of advanced signal processing and image reconstruction techniques to accelerate the data acquisition and improve image quality. Through a collaboration with the Department of Biochemistry at Cambridge, he realized the techniques he had developed for imaging could also be applied to NMR spectroscopy. And in 2015, he returned to the University of Canterbury in New Zealand, where a major focus of his research has been the development of the quantum mechanical model for quantitative NMR spectroscopy.
Okay, well, thanks very much, everyone, for being here this morning, and thanks, Mike and the Ivan team for arranging this. I think hopefully it'll be an interesting session. So my talk's going to be on the work we've been doing on quantum mechanical modeling for quantitative benchtop NMR. And this has really been a collaboration between myself and Eugene Matvichuk here at Canterbury, and Eric, who's going to be the second speaker, and one of his PhD students in particular, Alan Steimers, over in the University of Kaiserslautern. So I'm going to start by just sort of emphasizing where we're coming from with our approach to developing this quantitative NMR model. So quantitative NMR applies in a whole lot of industrial problems. You've got things like mixture analysis, reaction monitoring, adulteration detection, purity evaluation, process monitoring, and so on. And Mike's briefly touched on some of these earlier. But one of the things which is really important to remember with a lot of these problems is that ahead of the task that you're trying to do, you actually know what the chemical species are that you're going to be looking for. And so our approach to developing this quantitative quantum mechanical model was to basically make sure that we're using that information that we already know to enhance the analysis of the spectra. So we basically take this information that we know a set of chemical species as a given before we start the analysis. And then what we're looking to do is to try and determine the concentration of these components in a mixture. So we have this mixture, we want to know what percentage of this mixture is each of these different species. Now, NMR as a mixture analysis tool, as I'm sure you all know, is incredibly powerful. And traditionally, it's been done with these relatively large and expensive superconducting magnets. But over the last decade or so, there's been a real rise in these benchtop NMR instruments that have astonishingly good performance, considering their sort of the compact size and the relatively low price of them. But there is a bit of a downside to these benchtop systems, and that is that the analysis becomes a lot more complicated. So here I've got spectra for sugar on the left-hand side, and the analysis here, you have a whole series of relatively well-defined peaks, and so the analysis is somewhat straightforward. You can see it's still quite complicated, but you could imagine isolating individual components from that mixture. If we look at the same sample on a 43 megahertz benchtop method, all of the peaks associated with the different components here overlap, and it becomes very difficult to separate them. And so a traditional sort of integration method would really struggle in these sorts of applications. And this is what led us to the idea of doing some sort of model-based analysis, particularly a quantum mechanical one. And so the general idea of the model-based analysis is that you have some measured spectrum. So this would be the sort of blue line here. And then we have spectra associated with each of the different components. So orange, green, purple, and yellow in this case. And our measured spectrum is actually just given by a linear combination of the signatures of each of these individual components. Now, what we use is a Bayesian framework for describing that. And the reason for that is that although the spectrum is a linear combination of these individual components, each of these component spectra are characterized by a range of nonlinear parameters. And so to do a fit for any spectrum, you actually need to determine those nonlinear parameters before you can do the linear combination. And so we do that with a Bayesian framework. And so here what we're trying to do is to determine the probability of each of those nonlinear parameters by combining a likelihood and a prior. And so our likelihood basically describes how well the model fits the observation. And this is essentially a measure of the residual that Mike talked about just a few minutes ago. The prior is what information we know about the sample before we even start the measurement. And so this could be the typical range of chemical shift values that you might expect for different functional groups in a molecule. Or in fact, in most of our cases, we actually know that information much, much more specifically. And I'll come back to that in a little bit. But the heart of our model is really this quantum mechanical formulation. And the reason that we do this is that it allows us to reduce the number of parameters that we need to actually fit for each different component. And so just to illustrate sort of how this method works, at least just visually, if we take something simple like ethanol, then we have a chemical shift associated with these protons here and a chemical shift associated with these protons here. And there's some coupling between those. we can then use some pretty well-established maths to determine the Hamiltonian for those components and diagonalize that. And using that, we can predict what the quantum transition peaks would be based on just these three parameters. So 2 chemical shift values and 1 J coupling. And that will determine each of these different peak heights here. We can then combine that with a relaxation model to generate a signature of the model for any particular chemical. And the nice thing about this quantum mechanical formulation is that it really depends on the chemistry of the system. So we have knowledge of the molecule we're looking at and these parameters that describe it, and that generates our spectrum in combination with the field strength. We don't need to change the model in any other way, even when we change the field strength of the system. And that's a real powerful advantage of this quantum mechanical approach. And just as a sort of a real toy example, I'm going to illustrate why this really matters for a benchtop system. So we're going to make the molecule a little bit more complicated here and use a propanol. And what I'm going to do is look at varying the chemical shift associated with this group in the middle here. And we're going to vary it in a completely artificial way, but just to illustrate what happens to the spectrum. And so what you can see on the top is the spectrum at 400 megahertz, where we have a typical nice pattern of multiplets here. And then we can see the spectrum on the benchtop system. And even just with these initial values of these chemical shift parameters, we can see that the spectrum here is a whole lot more complicated. There's additional peaks forming on this group over here and this group here, and quite a few extra ones in this one in the middle. But then, since this is going to be, this is purely simulation, what we can do is then vary the chemical shift of this component in the middle and see how that changes the spectrum. And so what you'll see is that on the top here, there's basically no change as we alter that. The shape of the multiplets is not really affected by the chemical shift until they get very close to this one. On the bottom, though, that's very different. As we move this around, we get a lot of changes in the shapes here and also over here. And so the peaks that are associated with this group and this group are affected by the chemical shift of this group. But that's all captured by this quantum mechanical model. So even though we have this quite complicated system, we can still characterize it by, in this case, 3 chemical shift values and 2 J coupling values. Okay, so let's have a look at it at a real example. And so what we did here is we took some mixtures of alcohols and acetates. So we've got methanol, ethanol, methyl acetate, and ethyl acetate. And we ran samples on a 400 megahertz and a 43 megahertz system, and then we fit them with our quantum mechanical model. And if you look on the 400 megahertz system, you get nicely resolved peaks most of the way across. A little bit complicated here, but you could do this analysis by integration if you wanted, but our model works very nicely in this case as well. But then we take the model and we translate it down to the 43 megahertz, and you can use exactly the same parameters for the chemical shift and coupling parameters to describe the spectrum at 43 megahertz. And now what's really interesting is we can separate out these components over here where there is an awful lot of overlap of the different species in here. So this obviously shows you can do this. I want to very quickly, and hopefully this will work, demonstrate just how you would do it in practice with the software we've been working on. Now, unfortunately, there's something going wrong with my Zoom settings, so the resolution is not quite showing up the way it should do, but hopefully you can at least sort of see what we have. So what I've got here, I've got some samples that were loaded into the system. And I've set up our information here to tell us what the molecules are that are present in there. Now, you can't really see any of the parameters associated with this because of the problem with the resolution, but hopefully it'll at least give you a little bit of an idea. And then down here, I've got a graph which shows me what the actual composition is for this mixture. And so what you can see is the blue line here is the measured spectrum for this particular sample. And the red line is the current value of our model, a current best estimate of the model. And down the bottom here, we've got the residual. And at the moment, you can see that there's a pretty high residual here because these components or these peaks are not very well matched to the spectrum. And equally over here, we have not a very good match of some of these components here. So what we do if we want to try and fit them, we can try and just fit this using an automated fitting routine, but it's actually quite challenging to do that because it's a very peaky sort of optimization function that you have to try and evaluate. So the way we do it is actually to, for this sort of first go, would be to manually fit it. So we could click here, and these are the transition peaks associated with one of our components, and we can drag them around until they approximately match with the spectrum. You can see now the residuals improved. In fact, I did that remarkably well. It normally doesn't work quite that nicely. And you can do the same over here. And so we get that roughly lined up over there. Okay, and so now we've made a pretty big improvement. Model fits the data much better, but we also still would want to fit this a little bit better than that, so we can then go through the actual optimization fitting process. And this will vary a few of the different parameters of the model and try and just improve the overall quality of the fit. Hopefully that will get some of these chemical shift values lined up a little bit better than what I've got them at the moment by just eyeballing it. And so you can see it takes a few seconds to run. I have a bar here indicating the fitting routine. And yeah, now it's updated. Our residual is decreased a bit further. Unfortunately, it's rescaled a little bit, so you can't quite see how big it is, but we've got a pretty good agreement with between the measured spectrum and the model spectrum now. And this particular mixture was basically equal composition of each of the different components. And so you can see that's come out pretty close to where we'd expect it to be. And it was only roughly equal. So that's sort of how you would go about doing this for a new sample that you wanted to look at for the very first time. But that's actually a bit cumbersome if you've got a lot of samples to try and analyze. And so this is where the Bayesian framework is particularly powerful. So what we can do is if we have a range of different samples that we've measured, then we can learn how the chemical shift, for example, varies as a function of the composition of the mixture. So here we had about 20 different samples with different compositions of methanol, ethanol, methyl acetate, and ethyl acetate. And what we plot is the chemical shift of each of the different components in the spectrum as a function of the mole fraction of acetates in the mixture. And you can see that for most of the components, which we've got here, the chemical shift is reasonably stable, not changing very much. But unsurprisingly, for those OH peaks in the system, they're varying quite strongly through this sort of range here. So what we can then do is we can actually build this information into our algorithm. And so we can say that we know that if the mole fraction of acetates is, say, 0.6, then our OH chemical shift values will be somewhere here. If the mole fraction of acetates is about 0.2, then we'd expect them to be over here. And so that allows us to actually automate the fitting process. So we would initially estimate the mole fractions of the acetates, at least roughly, and then use that to estimate the chemical shift of the OH groups. And so just to see how this would work in a sort of automated routine, then we take our measured spectrum, something like this data here, and we can do a very crude initial fit based on our guesses of all the different chemical shift values for the components in the system. And you can see it does pretty well here. They're not perfect, but it's pretty good, and pretty good for the acetates. But this is where we've got our OH components, and clearly we're not fitting that very well. And if you look at then the estimated composition, it roughly matches with the gravimetric one, but it's not great. But then we can go through and we can fit these different components, these different chemical shift values that are pretty close, and we can get something which is getting a bit closer to the real result. we can march this forward a bit further, and then we can start to get estimates of what the OH composition, chemical shift would be. And you can see as we do this, we're getting improvements in these estimates of the composition. And then we run the fit on those OH components as well. And then we run a sort of a final fit at the end of that. And after that, you can see we get pretty good agreement between the estimated compositions here and our gravimetric composition over here. And so by incorporating this prior knowledge of the way in which the chemical shifts vary, that allows us to fully automate that model fitting process. Okay, so then let's have a look at a slightly more complicated mixture. In this case, we've got thiamine, pyridoxine, ascorbic acid, citric acid, glycine, and malic acid. And again, we can go through and we can fit these manually, and taking a little bit of time to do that. And we can identify the chemical shifts and the amounts of each of these different components in the system. And we can do that nicely at the 400 megahertz side, or equally at the 43 megahertz. But now this is a relatively complex mixture, and the way in which different chemical shifts are related to each other is not quite as straightforward as in that organic mixtures example I just gave you. So if we look at, say, one pair of chemical shifts, we have a chemical shift associated with malic acid and associated with citric acid, and these show a relatively nice linear correlation. So we could use this as a prior model to relate those two chemical shift values to each other. But we could also look at, say, two chemical shifts associated with thiamine, and these two are two chemical shifts that are relatively closely correlated together. And you can see we sort of have some sort of a linear variation with these, but it doesn't really capture a few of these different components. So it's not ideal in this case. But what we can also explore is how this varies in terms of three chemical shifts. And so we can look at correlations between these three protons here. And it turns out that these actually vary very nicely on a plane in this three-dimensional space. And if we rotate this around, you can see this very nicely. So they're all falling on a very simple line in a three-dimensional space. And then we can equally build that sort of a dependence into our model. And by doing that, that allows us to do a fully automated fit for all of those components too. And we basically characterize our distance from this line as what our prior is to do that fitting process. And so if we do that, then if we look at the sort of quantitative results from about 20 samples in each of these different systems, so we have high field results here using integration, our Bayesian model, and QGSD at MNOVA. So they work quite nicely on the high field. On the benchtop, we really couldn't get the QGSD method to work, and integration was pretty ineffective as well because of the severe overlap between the different components. We did build a PLSR model as well, and that sort of worked, but has a reasonably high error here. Whereas our Bayesian sort of auto-fitting method gave us an average error in this case, which was pretty comparable to what we got for the high field results using QGSD or our Bayesian model as well. And similarly, in the organic acids and vitamins system, we found that the integration, QGSD, and the Bayesian model were all basically equivalent to each other for the high field result. But again, on the benchtop data set, we could only use the Bayesian model. Integration and QGSD didn't really work. And we get almost as good error in that case, and significantly better than what we got with the PLSR model. Okay, so that was a few sort of toy examples. We then thought, well, let's try and do something a little bit tastier, and we took this into the Wine Research Institute, who are up in the top of the South Island of New Zealand. And so we actually took the instrument up there. This is their lab, and out the window you can see their test plots of their grapevines. And then we did some measurements of a variety of different wines that were available up there, and then built a model to analyze the components of wine. And so you can see that, or the results of that here. So we have this light blue trace is our measured spectrum. We have these big peaks associated with ethanol, which is obviously the main component other than water in the wine. But we also have a few other components that are present that overlap with this part of the spectrum. So we have fructose, glycerol, methanol, and glucose. And so we can extract all of those using this model as well. Down in this region, we have the organic acids. So we have citric acid, malic acid, succinic acid, and acetic acid. And again, we can quantify those with the model. And over in this region, we have lactic acid and alanine. We also have one component that we weren't able to identify to date, which overlaps with that as well. So we can pull out each of those. And so this one we just model by as a doublet of an unknown species. And so then we did a number of measurements with that. And then we actually gave this model to the group in Kaiserslautern, and they did some analysis by traditional sort of wet chemistry wine lab analysis. They also did benchtop NMR measurements and high field NMR measurements. And what you can see here is the results for one of their wines here, where we've got glucose, fructose, acetic acid, lactic acid, malic acid, tartaric acid, and glycerol shown. And in all cases, we get pretty good agreement between the benchtop results and the sort of traditional wet chemistry, which is really the gold standard here. And that does actually, in some cases, slightly better than the high field, which was analyzed by integration. But overall, the results from the benchtop and the high field are roughly comparable to each other. So it does vary a little bit from one sample to another. And I think Eric will talk a little bit more about what they're actually interested in using this for now in his talk in a few minutes. And that's really to try and see whether they can use benchtop NMR as a tool for process optimization in a wine setting. Okay, so that's all I wanted to say. Just really a summary of some of the things that we've been doing and a little introduction to our model. And I think the key thing is that this quantum mechanical modeling really enables remarkably accurate quantification from even very complicated benchtop NMR data sets. And the real strength of the model is that it's a field invariant method. So we can build up the parameters that describe the model by using high field data or data from spectral databases that already exist. And that's really what allows us to do some of the analysis of these really complicated mixtures that you might encounter. And with a little bit more work, once it's set up, you can automatically analyze batches of similar samples, and you can do that relatively quickly. So for one of those wine mixtures, for example, we can analyze those in about 5 minutes of computational time. Lastly, I just want to finish with a couple of acknowledgements. So a lot of this work was done here at Canterbury, and some of the people who helped with that are listed up on the top right here. And we were funded primarily by the Ministry of Business, Innovation and Employment here in New Zealand. I mentioned Eric and the team at University of Kaiserslautern, and that sort of really spun out of Hans Haas's lab, where Eric was based previously. So that's been a collaboration that's been going for a number of years now. But we've also been working with Magritech quite closely, and the University of Western Australia, where Mike Johns is based, and we did some analysis of sugar mixtures and honeys in conjunction with them. And we've also worked with Patrick Galvosis and the team up at the University of Wellington in the North Island of New Zealand. So I think I'll stop there. Yeah, happy to take any questions or pass back to Mike. I don't know how we're going to run this.
Okay, so Petrus has a question, and he's going to pose his question to you, Dan.
Yeah, I would be interested in hearing which NMR parameters you are actually optimizing during the fit. So are you optimizing chemical shifts, coupling constants, line shapes, the populations, of course, but other than that.
Yeah, so we do. So we primarily vary the chemical shift. We find that the J coupling constants don't change too much. So we do fit those as well, but the most important thing to get right is the chemical shift. Normally the J coupling constants are pretty stable, but we do also vary those as part of the process as well, and the relaxation parameters, we definitely vary those. Those are very important, and they affect your quantification very significantly.
Sure. So I'm just interested in you have developed this iterator in-house, or are you using some other program for that?
So the actual optimization routine is just it's a standard nonlinear parameter optimization. So that was built in Python. So the software is all written in Python at the moment. But the actual approach to how you do it is developed in-house. So and to do it for automated methods, that still does take a reasonable amount of development. So you can do the manual fitting reasonably nicely, but yeah, the automated one is a bit more challenging.
Yeah, just because we have an iterator here at an NMR solution, so I'm just interested in hearing what other people are doing. So if you want to have a discussion for this, then please reach out. We are happy to talk. Me and Matthias Niemitz. I don't know whether or not you've met him already. So
yeah, no, that sounds fantastic. Definitely happy to have a chat.
Good.
Thanks,
So
Peter.
if somebody else has questions, then I yield the floor to them.
Thanks. Okay, so I'll see
A couple of questions, if I may.
Yeah, go ahead.
Daniel, great talk. I really enjoyed it. Actually, I have a couple of questions I'd like to ask. So the first one is your fitting approach sensitive to phase and baseline imperfections?
So we actually fit those as part of the model as well. Sometimes you can, sometimes that can cause problems, but most of the time we find that it works pretty nicely. So we just have a fairly standard automatic phasing routine, and then as we adjust those parameters, that mostly seems to account for it. We do, when we have like a large solvent peak, for example, we fit that, but we usually fit that and sort of ignore the solvent contribution. So we use that more as a baseline fitting tool, as opposed to really trying to fit that solvent peak perfectly.
Great. And then my next question is, does this approach work past simple pulse acquire experiments? You know, maybe you have a CPMG period or something that has some sort of, J coupling evolution, maybe you have a little anti-phase magnetization in there.
So theoretically, yes, I think it should do, but we haven't got that set up yet. So we have done some diffusion measurements, and I think Eric will talk a little bit about that. But even in those diffusion measurements, we actually had to set them up such that we minimize the sort of more the complexity of it, and we only treat it as a pulse acquire in the way that we model it. But in theory, you should be able to do that. We just haven't yet.
Got it. And then since you're using a Bayesian approach, I guess the natural question to ask here is why not do this in the time domain?
So actually you can, we've got it set up so you can do it in time domain or frequency domain. But what we find is that the frequency domain is better because it allows you to select out just the parts of the spectrum that you're interested in analyzing at any one time. Now you can do that also in the time domain, like they really are equivalent. So it really doesn't make a massive difference which way you do it, but we found that it was a bit nicer to set it up in a frequency domain. But we do it both ways, and it really doesn't make a big difference.
Got it. And then my last question, in reference to the slide you showed where you were comparing results by the Wine Lab, Benchtop NMR, and Highfield NMR, I noticed that for fructose, there was a significant difference between the Highfield NMR result and the other two. Can you comment on that?
Yeah, so the sugars are really tough in wine, right? The sugars are present very low concentrations for most wines, particularly dry wines. Sweet wines, they're relatively easy, but for dry wines, they tend to be present at very low concentrations, and they very significantly overlap with the water and the ethanol peaks. And so fitting those sugars is really challenging. I think in the case of the Highfield, that just basically means that the integration type approach was a bit more of a challenge for those. And it's also a problem for us. So, they're just difficult. So we have a relatively large error on those sugars when they're present and overlapping with all these other components. It probably doesn't show up very well on the way that was plotted, but you really are trying to fit something that's very much towards the baseline in that.
Thank you very much.
Thanks, Gennady.
Just can I ask make one comment? This is Krish.
Yeah.
Just follow up on your answer, Dan. Follow up on your answer to Gennady's question. Even in time domain, regional analysis is pretty straightforward as well. We do that routinely with our software.
Yeah, sorry, I didn't mean to imply you don't. As I say, we do the same, but we just found it easier in the frequency domain. It really doesn't make a big difference, I don't think.
Okay, is that okay, Krish?
Yes, thank you.
Okay, great. So thanks very much indeed, Dan. And I'm going to introduce our second main speaker, who is Eric van Habu. And Eric is going to be giving a talk that follows on from Dan's, and it's titled Process Analysis for Benchtop NMR Spectroscopy. So by way of introduction, Eric holds the chair of separation science and technology in the Laboratory of Reaction and Fluid Process Engineering at TU Kaiserslautern in Germany. He started his academic career with a diploma in chemical engineering from Technical University of Hamburg-Harburg, which he followed with a PhD from Kaiserslautern. So he held a postdoctoral position at Cambridge University, and he returned to Germany to take up a position in industry at BASF. And he's presently a faculty member at Kaiserslautern, as I said at the start. And he's got an active group of scientists, and he also obviously collaborates because he's going to be talking about that today. So with that, I'd like to invite Eric to take over the screen and give his presentation, please.
Yeah, thank you, Mike, for the nice introduction. Also from my side, welcome to my talk. Thank you very much for inviting me, and thank you very much, Mike, for the introduction. As already said, I'm from the university in Kaiserslautern. I'm pretty sure that you don't know this small town of Kaiserslautern in Germany. It's in the southwest of Germany. Some of you might have heard about the airbase Ramstein, which is very close to us. So this is where it's situated. Before I show you how we use Dan's or the nice tool developed by Dan and his group, I would like to introduce you or to explain you why we are using NMR spectroscopy. Because as you have heard from Mike, I'm really a chemical engineer. I was working for 3 years at BASF in designing reactors, and you might ask yourself, why is somebody who's designing reactors, why does he need NMR spectroscopy? So why is it so useful for us? Because it has many nice features which really appreciate, especially the first one. It's, as you all know, we can use it to elucidate reaction networks to really understand what are intermediates, what are the side products, where might arise problems in the process. And another factor which is very important for us is we can use NMR spectroscopy to understand the dynamics of processes. For example, we already seen some examples, reaction kinetics, problems with mass transfer, or what could also be very interesting, like transient separation processes. On the right-hand side, you see an example. This is a chromatographic process. And basically, you see here the different retention times of different components here on the time axis. And here you see the different components. If you would have used here standard UV detector, for example, you will never be able to distinguish between these different samples, different species. But with an NMR spectroscopy, you get this chemical dimension, and you can use this chemical dimension to get more insights into your process. So this is where we really like to use NMR spectroscopy, where it really benefits us. But of course, there are some requirements, and basically, because NMR fulfills these requirements, we are using NMR spectroscopy. Especially the one is we have to do the analysis under real condition. What do I mean with a real condition? Real conditions are basically the same pressure, temperature, and composition as we have in the real technical process. Especially when you analyze reactions, when you have to look at them, get different results, or different pressures, you can get different results. So you really have to need the same. We have to use the same to look at them in the same condition as in the real process. And often we're not only interested in the information is what is in there, we also need the information how much is in there. So we need quantitative analysis, for example, to get real reaction kinetics, to get real composition, how this behaves. And of course, in order to get this, and on this the example on the right-hand side is a very good example for that, we need high temporal and high chemical resolution to achieve all this. So all in all, we can say, and you all know this better than me, that NMR spectroscopy fulfills many of these requirements, and that's why it's a very good choice for process analysis. Here, I give you an example where I use this. This is an example, maybe some of you have already seen this because I've presented this several times on panic, for example. But this shows very nicely where we tied in NMR spectroscopy to get a better understanding of process. So this was an industrial collaboration, and they wanted to know more details about this process. I don't go into details. It's a process to produce croton aldehyde. It's an intermediate in the, for example, intermediate in the value chain for vitamin E. And they had some problems with the process, and they want to optimize the process. And then they came to us and asked us to help. And we looked in the literature about this process, and basically this is the thermodynamic or reaction representation of the process, what you find in the literature. So these are different components and different reactions which they run. So then we run through a full analysis with NMR spectroscopy. We found a very different picture of the whole process and found, okay, there are much more components than the literature thinks there are, and also much more reactions. And you can quite easily imagine if you have this information, then you are then really then you can use this information to optimize the process, or maybe use it also for troubleshooting. Without this information, if you don't know that there are some byproducts or some intermediates, it's very difficult to get any improvements in this process. But as I said, we not only need to know the information, what is in there, we also need the quantitative analysis. So at the end, that we can build some nice thermodynamic models, for example, and to get really some species distribution. So this is a very nice example where we can use NMR spectroscopy to get both qualitative results, such as elucidation of reaction networks, and quantitative results to really improve our models, and then use this model to improve the process. And most time we used, or like the years back, we often used high field spectrometers to get our results. The problem is with high field spectrometers, as Dan already showed you, I mean, you all know this, they're expensive and you need dedicated labs, but especially when you use them for process analysis, they are not, let's say, there are no standard equipment. So often you have either to buy special equipment or you have to do it yourself. And this is very tedious and also often very expensive. So I show you some example where we built our own special devices to really, for example, here we measured the absorption of CO2 under high pressure into an amine solution. Yeah, but this is a home-built equipment, and here this is a special probe that we developed to follow fast reaction kinetics. Very nice equipment, but yeah, it's very tedious. So the problem is, which you all know, at the end you have to bring the process into the NMR spectrometer, and a typical process labs do not have these spectrometers available. For example, at BASF, where I worked, there are many process labs, but the NMR lab, which is very large at BASF in Ludwigshafen, I mean, they have, I think, more than 10 NMR spectrometers available, but they're on a different building on the very other side of the site, 2 or 3 kilometers far away from the process labs. So you'll never be able to do really online process analysis if the lab is not where you run your processes. And of course, there is where we really like to tie in benchtop NMR spectroscopy, because with these benchtop spectrometer, we can bring them to the process. Here you see some examples. On the left-hand side, this is a batch distillation column, which is sitting here in a fume hood. And you see here the benchtop spectrometer just connected next to this. Or here we place the whole device into the fume hood, and here you have a small reactor and a distillation column here, and you see how you can really interconnect the process with the spectrometer. So it's much easier. Of course, there's still some problems like the time lag between the process and the spectrometer, or temperature and pressure control. I mean, I won't talk about these today, and especially because these are very nice, let's say, problems which chemical engineers really like to tackle. There are the other problems, which Dan already mentioned, and also Mike mentioned. We have the other problem from the analysis side point of view. We have large areas of spectra, and often the spectra have a very poor quality, especially when you use benchtop spectrometers. And this is exactly the point where we tie in Dan's very nice, nice software. Here, I would like to give you an example where we use the software or the approach Dan presented to analyze a complex reaction network. I mean, still, it's not that complex, and it's still maybe a little boring reaction, but it's a perfect reaction which you can use in universities because it's no harmful substances. So this is the esterification of glycerol with acetic acid, but you still see you have several intermediates in the process. And you see also the intermediates are chemically very similar. And we wanted to follow this reaction kinetics of this reaction systems. So here you see now the time series, which we got from the benchtop spectrometer. And you see exactly these typical features. So you have overlapping peaks, very small peaks, very big large peaks. And you see the whole time series. So it's not only one spectrum, and there are many, many spectra. And now you see one selected spectrum. So you have the large piece, this is the OH group. This is the acetic acid, the acetate group here, which you see. And this is the interesting region. And now if you zoom in, you really see the spectrum looks awful. Yeah, it's very difficult to analyze the spectrum. It's not only one, but many. And now you see results by the software developed by Dan's group. So here the gray line is the original spectrum. So this is the high field. And from the high field, we really get the information about the chemical shifts, about all the species. And we see that we get a very nice fit here. Then, as Dan showed, we can translate this information into the lower fields, like the benchtop spectrum. And then we can use this information as prior to get very nice fits. And again, you see here, this gray line is the original spectrum. And then you see the fits of the different species. So the glycerol and the different intermediates here. And then you can see at the end, we get a very, very nice fit. From this, we can really follow the course of reaction. And so this is here basically the concentration, and this is the time. The circles are the high field data, and the diamonds are the benchtop data. And you see they're basically the same information. And you see really this is a textbook example of consecutive reactions and parallel reactions. You can really see the different features here. So you can really see that, for example, this is a consecutive product, and you can really get many information from this concentration profiles. And so you see this is at the end, it's very simple. We just put this into the benchtop, fill the sample in, let the reaction run, and then afterwards we can do this analysis pretty like us, push the button. Then if you want more quantitative information, for example, you want to get now really kinetic information from this. So how fast is the reaction? At the end, you want to have a kinetic model. They can use even more information. So here we analyzed another reaction, also a very simple one. It's the hydrolysis of acetic anhydride. Here you see the spectra, which we acquired with the benchtop. And here we connected a batch reactor to the benchtop. And this is, at the end, the concentration change over time, which we get if we analyze these spectrum by spectrum by spectrum in a sequential way, as I showed before. So this is, we use the approach or the method presented by Dan but we did it in a sequential way. And as Dan already mentioned or pointed out, the Bayesian approach is very nice to tie in more information, prior information you have on the system. And here we have a special information. For example, we know we have a chemical reaction going on, and it's not the change from one spectrum to another spectrum. It's not just arbitrary, it follows a rule. And we say it follows a reaction kinetics. So at the end, what we do, we use the information on the reaction kinetics. So the kinetic law is a prior, and we say, and this is here basically the idea, we say, no, if we analyze everything simultaneously, so all spectra are analyzed simultaneously together with the information of the first order reaction, and then we get directly our information on the kinetics from the fit. So we fit basically the amplitudes and the chemical reaction in one go. So the kinetic parameters in one go. And then at the end, you see we get a very smooth line. And here on the right-hand side, you see with the real data. So the red points are the sequential approach. The blue points are the simultaneous approach. You can really see how we can improve the accuracy or the uncertainties. We can minimize the uncertainties of our results. So this is a very nice example where we can tie in additional information which we have, like prior information, to improve our results by using this nice Bayesian method. Here's another example, as Dan already mentioned. We used this also for diffusion measurements. It follows the exact same idea as for the kinetic measurements. So here it's not the time as additional information, this is the gradient strength, and then we acquire basically you can see this as a sequence of spectra which we acquire. Now we could, in theory, analyze spectrum by spectrum by spectrum, and then you get this plot here, and then you fit to this plot, you fit your equation to get the diffusion coefficient, or you could just use this as prior information and do the simultaneous approach. Then you see they have to follow all this line. So you tie in this information to get a higher improvement or better results. Basically, you get a better first guess for your results. So you get better fitting results. And we use this to analyze the diffusion coefficients of a complex mixture. This is a little bit a random mixture which we filled in several samples we found in our lab. So this is an amine, this is glycerol, propylene glycol, ethanol, acetic acid, acetonitrile, water, and mixed them. You see here again the high fit spectrum, the Benchtop spectrum. You see there are many components. And also quite complex features, which you can also see here. And then we analyzed the diffusion coefficient. You see here a parity plot. So this is the diffusion coefficient measured by Benchtop. This is the diffusion coefficient measured by Highfield. And you see the different components here. And what you can see that basically with very, very good agreement between Highfield and Benchtop. So here are more information about the uncertainties we got. But you see, by just pushing the button, where very quick analysis method, and you get pretty good results on the diffusion coefficients, for example, to distinguish the different species or to get more information about the species here in the system. So again, a very nice information where we use prior information to improve our results and get basically from a spectrum where you think, oh, normally there's no way of getting information out of this, but here you still can do it because you have prior information of the spectrum. Here, there's another example. As Dan already mentioned, we continued this analysis of wine. Unfortunately, this is something in German here, but it's not so important. So we really use this tool for improvement of the fermentation process. So this is a very nice example of an idea which the colleagues of the Wine Institute, which we're collaborating with, had. They wanted to improve the quality of ice wine. I don't know if you know ice wine. Ice wine is the wine when you pick the grapes when it's frozen. So they have a very, very high sugar content in the grape. And normally, as you know, the fermentation in wine is done in batch. The problem is if you do this batch process, you get a very high concentration of sugar, and this high concentration of sugar is stress for the yeast. And then the yeast also tend to make byproducts, for example, acetic acid. As a chemical engineer, this is quite standard, this problem. So what you can do then, use another feed strategy. Just instead of a batch process, you use a fed batch process. So basically, step by step, you add a little bit of this fruit juice, of this grape juice. And by this, you can reduce the concentration of sugar and the goal is to get less byproducts. And this is like a setup which we use to test this strategy. These are very, very rough results. So these are just results we got a few weeks ago. So sorry for the bad quality, but I hope you get the idea. So, and we use now the benchtop spectrometer to analyze the difference between the two feed strategies. So the blue one is the traditional feed strategy, is the batch fermentation. The red one is the fat batch fermentation. Here you see the time, here you see the concentration of different species, so acetic acid, ethanol, and glycerol production. And this is the first go, so quite a kind of quick and dirty approach. So there was no optimization of the feed strategy, just we wanted to see, can we use this approach to really see differences? And you see immediately, you see differences. You see here, for example, the acetic acid production, how it's significantly lower here. At the end, something happened, I don't know what, but yeah, but you can see, you can really follow the differences, and it's pretty simple setup. Yeah, you don't have to fiddle around. You can use it directly to improve results and really follow the process. And now we, for example, we could improve our feed strategy by comparing different results. So I think this is a very, very nice example where we can really use this approach, because especially in the wine industry, this is, at least in Germany, it's very regional, very small industry, like these are just small farmers, and they will never be able to afford a high field spectrometers. But for a kind of small research institute, they could afford a benchtop spectrometer. So benchtop spectrometers could be quite a game changer here in this field, because basically at the end they can really follow process and get a better understanding what is going on in the wine. With this, I would like to finish my talk. I showed you that the benchtop devices really simplify our way how we want to look into processes, because we can much easier connect the spectrometer with the process as it is possible with high field spectrometers. But of course, we face several difficulties when we analyze these spectra. But prior knowledge really helps to improve the results. And if we do this, we do the combination of benchtop NMR spectroscopy with this advanced analysis tool, as Dan showed, we get the combination is then a very nice and very versatile tool in many, many areas, and you can use it in many fields to really get better results. Yeah, with this, I would like to thank you for your attention. I would like to thank me for inviting me, and especially I want to thank Ellen, because she did all the work which I now was allowed to present. Thank you very much.
Thank you, Eric. That was really great. I'll ask a quick question as my prerogative as the host to chime in first. So in the case where you've included your kinetic equation together with your data, is there a risk of overfitting there, and potentially if you used, for example, the wrong kinetic equation, would it fit? Yes, this is a very, very good question. And it's, I mean, the same as always, garbage in, garbage out, yeah. So if you have the wrong equation, of course, yeah, then it won't approve at all. For example, we tried the same approach for the esterification of glycerol, and the kinetic model or we used basically the wrong kinetic model, or the kinetic model is very complex because you have several reactions, and there it doesn't work that nicely, or you don't get any benefit of using that. So of course, you need to know that your model, which you used to as prior, has to be correct. Yeah. Right. So this is always a kind of, yeah, does it help you or not? But the nice thing, I mean, you can give it a try and see if it works. And by this, if you give it a try, then you also can see, is the model correct? Because you see it quite immediately. In the acetic acid anhydride system, we saw, okay, obviously it is an improvement. This also gives you, obviously the model is correct. But if you see it doesn't work, then you get also information about your model and say, oh, maybe the model is not that good. Right. Okay. So you wouldn't get convergence if you had the incorrect kinetic model. Yeah. Okay. So there's a few questions from Michal. I'm not sure if I can pronounce your last respondek. Would you like to turn your mic on, Michal, and pose your questions?
Yep. So I had a question to Eric. I'm interested in the online Benchtop NMR path, so process analytical technology. Is it something you bought? It's commercially available, or you build it yourself? If you have some photos, maybe you could share it.
Yeah, of course. The setup itself was built in our lab, but basically to connect it, it's pretty simple. So also the vendors, they often they can buy also pumps and equipment to connect to for example, any reactors or batch reactor or any process. But we found at the end it's often up to you to make special arrangements. So that's why at the end everything was mostly home built and done by ourselves. But it's really not difficult because you can use the standard equipment which you have in laboratories. There's always the problem when you connect the spectrometer to a process, all this problem about flowing samples and this
Right.
difference of stop flow and flow measurements. But if you play a little bit around and then it's often not so difficult. The most difficult point for us, especially with the Benchtop spectrometers, is the temperature control. Because all this problem that in Benchtop spectrometers, as far as I know, up to date, you can't control the temperature inside the spectrometers. So there you face some problems, which is still unsolved. But for example, in the wine process, it doesn't matter. Yeah.
Thank you.
I can perhaps add as well on the topic. I think Michael Myvold at BUM has built a PAT compatible and set up in an explosion-proof cabinet, and I believe he's reported that. So there is work going on to build these in a kind of a PAT compliant manner.
Yes, we had also our colleagues of mine at BASF. They had a process with an analysis. Susan Riegel was involved in that. There was also, it was really built into a FUMUD, and they had a very nice way to basically do this automatically, so that there was a pump and it filled in the sample into the spectrometer or the line, and then it sucked it out again, and after 5 minutes it filled it in again. And so by this there was an automatic way to pump in and suck out samples into the spectrometer. So this is a little bit of fiddling and a little bit of playing around with like pumps and sucking out, but switching valves automatically, but it can be done. Yeah.
Cool. Michael, do you want to ask your second question to Dan, and then we'll move to Maria?
Yes, I can do that. So to Daniel Holland, I have a question, and that's about the accuracy of your software when you have very, very low signal to noise. And here I just use this definition of limit of quantification signal to noise around 10.
So generally, it's actually very robust to low signal to noise. And one thing to remember is it's, the way that we model it, your signal to noise should be defined based on essentially the integral of the peak as opposed to the peak height. If you just use the peak height, that's a little bit misleading. So what is say a 10-to-1 peak height for a very narrow peak is much harder than a 10-to-1 peak height for a broad peak, because the integral area is much lower for that one. So that's often we define signal to noise based on peak height, and as I say, that's a bit misleading when you've got the model-based approach. But as a general rule, it's pretty robust. So we did a test actually with this diffusion example that Eric was talking about, where we just kept adding noise, and it really, we had to get it so noisy that you almost couldn't see anything before it really failed. It was remarkably robust to that.
What percentage of accuracy are we talking here? Like 1%, below that?
So it always depends. So for us, 1% is what we have typically been trying to target, and that's around that 1% level is normally around the model fitting error. So actually we run it at about I say 1,000 signal to noise, and you get about 1% error. You could do it at 100 and it would be about the same. So it's only really once you get down to around 10, maybe that error starts going up a little bit. So it does still get affected by that noise level. But I don't have a figure to say exactly what it would be for a particular signal to noise level. It's very problem dependent.
Thank you.
Okay. Thanks, Michael. Marivi, do you want to unmute your mic?
Yes. Can you listen to me? Can you hear me?
Yes, yes.
Good. Never know with the speakerphones. Anyway, so this has been a fantastic workshop. I really enjoy. I'm working a lot on reaction monitoring. We are not using anymore the classical equations to look into first order, second order, and zero order. We're using all these RPKAs, or reaction progress kinetic analysis, and BTNA, variable time normalization analysis, where we can obtain not only the reaction rates, we also can obtain the orders for individual species. That can be 0.5, can be a half number, or any other number, which give us information sometimes if there's polymerization or something. So have you used those techniques? They're really very helpful because it doesn't fit on the first order, second order, or zero order. We found a lot of information on the mechanism of the reaction, just understanding what is the order of the species.
That's a very good point. I think we could use it very nicely for the glycerol esterification example. But for the other one, we just did a very quick and dirty try. Let's try a first order law and it worked perfectly. And it's also understandable why it works so perfectly, because it's highly diluted in water. So it makes sense that it's first order. But of course, I see your point, because the more complex example, there's much more difficult to get the reaction orders, and an approach as you suggested would be very helpful.
Yeah, we also even got negative orders on reaction.
Yeah, of course. Yeah.
So it's really very interesting, and it's so I would advise you to look. It has been a learning from me, because I'm working with an expertise on kinetics. And that's how I learned those things myself that I didn't know at all. So, but thank you.
Thank you. Yeah.
Thanks, Marivi. So there's an outstanding question from Richard Vestandi, who I think has left the meeting, but I'll ask his question nonetheless, and it goes to Dan. And the question is the software ready for implementation with Magritech software, or is there a way to try the software?
So we're working on that. So we have just this last summer been setting up a package to integrate it with the QNMR thing there. It's still unfortunately a little way away from being ready for that. So full integration with their system is probably a little way off yet. And unfortunately, the person who's doing that no longer working with us. So I don't know when exactly that will happen, but that is on our to-do list. But we also do have a package that we can share with people. So if people just want to get in touch with me, that's probably the easiest way to do it. And I'm happy to try and work with them to see if we can apply it for different things.
Great. So I have a question for Dan. How long does it take to develop a model for a new compound?
So, I mean, that's a good question. It's also a difficult one to answer. So it does depend very much on the system. We have it set up now so that we can basically use the NMR prediction software to identify what the probable chemical shift in J coupling parameters is going to be for a model. And that allows us to get a pretty good start for any new molecule reasonably quickly. So say, I don't know, 20 minutes or something like that. Okay. But then depends a little bit on how many different species you have and how similar they are as to whether you can assign peaks correctly to different components. And if you have the high field data, that obviously makes things a lot easier. So we have done some where we have no high field data. In fact, I think this glycerol example, although we had the high field data, we analyzed it without using any of that. So you can do it there, but it is a bit more challenging.
Sure. Okay, cool. Maybe one for both of you or either of you. So you had one example where you had an unknown component and you simply said that was a doublet. But what if you had an unknown component, for example, a side product, and that had more multiplets in the spectrum? How would you deal with that?
So I think maybe I would go. So the first way we would look at it would be to fit all the components that you do know that are present, and then that would allow you to get a somewhat cleaner sort of spectrum, but by looking at the residual. And then I think you have to see whether you can exclude them by just not analyzing that part of the spectrum, or even better, see if you can do something to actually identify what those components are. So sometimes, depending on the complexity of the model, or of the spectrum, I should say, you can infer what that likely model or likely component would be. Typically in a reaction, you know the sort of things that could form, and so that allows you to sort of guide your interpretation of it.
Right.
I don't know, Eric, do you have anything else you want to add?
Perfect answer. I mean, this is also a question. I mean, basically, we have to admit the main idea of this approach that you have prior knowledge. Yeah. But I think it's in many cases it's also reasonable to assume that you have prior knowledge. Let's take the wine example. I mean, we can analyze a wine with a high field spectrometer, so you get very good information about what is in the wine, and then afterwards you can use the benchtop. So and wine also, of course, it changed a little bit, but the main composition of wine is that in this respect pretty similar. So it's a very good example where you can use this. And for example, we want to use it also we were just setting out a project where we want to use this for to detect mold in wine. When they deliver the grapes to the vineyards, they need a very fast detection method about the quality of the grapes, yeah, and it must be very fast. And so far they use FTIR, and they have problems with that, and they're suggesting to use their Benchtop NMR spectroscopy, which could be very interesting. So there, I think you can just avoid this problem by getting high quality data from, for example, high field. But of course, there are examples where you can't use this, and this is where you get problems. But I mean, without this method, you have the same problem because you simply don't know what's in there. A colleague of mine, he's now using a very nice approach based on machine learning, and he uses information from databases to basically get a fingerprint of an unknown spectrum, and then this method suggests what could be in there and gives you basically a kind of hint in that you could use this. And at the moment we're discussing this, if there's not a possibility to connect these two methods, like the Bayesian approach and this other method, like they call it NEAT because it's a NEAT method, to detect unknown species in spectra.
Right. So if you had an unknown species, would the software tell you what the spin system is, even if it doesn't know what the compound is?
Not at the moment, but I think that's sort of what Eric's suggesting we want to be able to get to. Yeah.
Okay. Okay, guys, we're on the half hour, and I suggest that it's a good time. I know it's a good time for us to wrap up and go our ways. And so I'll end by thanking everyone, the Island Committee, for allowing us the time to hog the agenda today. Many thanks to Dave and Grish and the entire team for the opportunity. And my special thanks goes to Dan and Eric today for beautifully presented and beautiful science. It was an absolute pleasure to watch. So thank you one and all.
Okay.
Thank you very much.
I'll speak up here, and I also thank our three panelists, Michael, Daniel, and Eric. And John Webb said that he had to leave early, but he sends his regards to everyone. And I think this is another great meeting. And so with that, if there are no other questions or comments, I'll adjourn. Okay. So see you everyone next month.
Thanks, everyone.
Okay.
Bye-bye.
Bye.